this is Ryan, goes by the name of Guspo on GitHub, and me, Andre, go by the name of Treeform. And we're going to talk about the technical details of our JPEG decoder for the Pixie name library.
Very exciting.
Yeah, really exciting. So let's start with talking about STB image, right? It's a pretty awesome
Sure.
library, right? It has served us a long time.
Yeah. When we first fought with JPEG, it didn't go so great. Plugged that in, and everything worked for like a year.
Yeah.
So it really did work well for us. However, it wasn't quite perfect.
Yeah, we had some issues with like file paths on Windows, it uses a different way to read files on Windows than NIM does, and there was like, I don't know, we couldn't figure it out. We just used the memory interface and it was fine. Yeah, and then you ran into a problem with the DLL.
Yeah. So one of the things we like to do is make our libraries available to other languages through bindings, which means we build DLLs. And not everybody was having an issue with it, but some people were, and it was unusual. So just kind of yet another. I'm sure we could have figured it out, but it turns out it's more fun to just write a new decoder.
Yeah, I think the main thing is that on GitHub, when we had the Pixie, it showed that half of it is written in C, which was false, and it wasn't even our code, right?
Yeah,
It made
that's
us
a
feel
really good
bad.
point.
No one
Here
cared.
we are.
No one
Yeah,
cared.
we're saying we're trying to write a pure nim library, and GitHub is busy saying everybody it's a half C library.
Exactly, because
We're like, well, not really. I mean, kind of, but not really. So
yeah, STB has an awesome license. It's like very permissive, so it's very easy to shove it in all the projects. But we want to do something, because you just think this stuff is cool, right? You're like really into all those file formats and images and graphics and etc.
Well, we've talked about this before. I think we have enjoyed learning how things actually work, and a lot of these things aren't implemented in nim already, and so it gives us license to kind of bring a pure nim implementation to people. And there is benefits to that, not just us understanding it, but it's really easy for people to integrate into their projects, and they don't have to worry about mixing C that was expected to compile under certain circumstances, and now they want to do it in ARM, and maybe that's weird or something. Nim just kind of helps iron a little bit of that out. So
Yeah, I don't know. Maybe it's just us, but I do find the NIM code much easier to read than C code, right? And specifically, our implementations, because STB does use a lot of like pointer walking, and a lot of times you like don't really know where you're at. You just like staring at a pointer that's reading a number, right? But we follow more normal NIM conventions. We have objects and like they contain stuff inside of them, so it's kind of more
yeah,
clear where the data is coming from.
yeah. I totally agree. Nim is way more readable, and I certainly think it handles pointer stuff much better. In some of these file formats, I do feel like we still end up, at least I, drag us down into pointer land sometimes, but there's always a reason for it, and I think still Nim helps a lot there. So,
Yeah.
yeah.
Yeah, for sure. Yeah, I think maybe if I was like more comfortable with CN pointers, like the STB format wasn't such, wouldn't be such confusing to me, but it was very confusing to me.
Yeah. Yep, totally. I think we just got really good nim pattern matchers, and we see C, and it's like,
Yeah, so just like, what is this pointers? Everywhere, just pointers, and they're just inking and decking them. How does this work?
But yeah, so STB image, like you said, it really did serve us well. But in the end, we went to war with JPEG a second time. So actually, the second time Andre went to war with it, and he succeeded in defeating what I think are the really kind of difficult parts of JPEG, which is handling the progressive and restart markers and some of that, which we'll get to as we dive into the details here. But yeah, this was a little bit troublesome for us to get done, but in the end, we won, and I think we're pretty proud of that. So
Yeah, I think I'm pretty proud of this, project. Yeah.
So I think it was a thing worth fighting because JPEG is very common. Like you could argue it's probably the most common image format out there. Every camera takes JPEGs. JPEG is a pretty big deal, and so it's not like we did some niche file format here. We're doing the big daddy.
Yeah,
and
I would say the three most common formats on the web are PNG, JPEG, and GIFs, right? And we support all three of them now, right? Which is just great. And like JPEG was like the last holdout, right?
Yeah,
Out of the big
toughest
three.
one,
Yeah,
for sure.
For sure. Yeah.
But and even though we're talking about how tough it was to decode, I think there's a really good video that we have found that helps explain it. But it's because smart people figured out really clever ways to make an image file really small without losing, I think, quality, and it's genuinely extremely clever. And so even though it was a real pain in the butt for us to decode it, it wasn't because people did crazy things for no reason. It was because the binary file format itself was maybe more troublesome, not that the ideas were bad.
Yeah, exactly. I 100% agree. I think like the ideas behind JPEG is really cool. And again, watch this video if you want to find out why they did it and maybe more in detail how. We'll touch briefly here, but really this is more about our implementation and what JPEG is. This video is about what JPEG is.
Would
really,
you
really
maybe
cool.
what is the actual title of that video? Do we remember that?
I
can
don't know.
look it up real quick.
I know. We'll have the link available.
Yeah, we'll link it in the description. That's a good point. Okay.
Yeah. For us, it's just the JPEG video.
Yeah. Both Wilson, I think 2 or 3 times. It's very good.
Exactly. Yeah. An interesting thing is though, the first time I watched it, I felt like I did not get it. Only after I made the full implementation, I now get it. Right? It's kind of funny that way. It's like basically they showed us how to. Well, the author in the video showed us how to do the JPEGs, but like we only I could. Basically, just watching it after I've implemented everything, only then I kind of got it 100%. Before, it was just like, performance or art or something, right? But only after fighting the fight.
And it's still a great video, so I really do encourage people to watch it. I think that what we can do here as we talk through it next is try to explain what a programmer might be missing from the video that helps it click, right? Because the video is not strictly made for programmers, and so we can maybe add that tiny little piece that will help.
Yeah.
So,
yeah, and I think also video starts up with encoding a JPEG, right? Which is not what we're doing. We do not have an encoder. We only have a decoder, right? Yeah. Which is hard enough.
Plenty hard enough. Yes.
Yeah. All right, moving on next.
Yeah.
So let's look at like the process, right? That you kind of use to decode a JPEG, right? So I guess JPEGs are divided. When an image comes in, it usually comes in RGB channels, right?
Yeah.
And what JPEG I think is really clever, what it does is it converts us to this like chromulence, blue luminance, and red chromulence, right? Blue chromulence, red chromulence, and luminance, right?
Yeah.
Basically, these 3 channels that at first hand didn't make sense to me, like why I was doing that, right?
Yeah.
But once I saw it, it like really clicked. I think it's like really clever. Right, and so what it does, let me show you an example how it looks like from the video, right, is that luminance is basically like the grayscale version of the image, but not quite. It has slight tint of color to it, but it's almost like grayscale, right? And then the red and the blue are kind of like the red and the blue color with all of the borders or like all the shadowing removed, right?
Yeah.
So they come up like really washed out, and a lot of times it's like really hard to see what's even in it, right? Because it's just all like just splotches, right, of color, right?
If you just saw the red chrominance or the blue chrominance and nothing else, a lot of images would just look like noise. You wouldn't even know what it was.
Yeah, so. And they look like extremely flat, right? Like extremely, right? And that's exactly because all of the like heights and valleys and shadows are all in the luminance, right? And I think this is like really, really clever because then what they do with the red and the blue chromulence is just scale them. They can scale them like way less than the luminance, right?
Way down, yeah.
Way down. So it's like a huge saving in space.
Yeah. So if instead of having like 1R, 1G, and 1B for every pixel, you could have like 1 luminance and then like maybe a quarter of a G and a B.
Exactly.
So just this step, it like halves potentially even like 1/3 or 2/3 reduction of your file. Like just this can go that far.
Yeah,
and that's only one of the tricks they have.
Exactly, they have so many tricks.
It's a good trick. It's a good trick.
Yeah.
So
I think like this is maybe one of my favorite tricks. Well, it's so easy to understand, right? Like for like understanding, like this is just a really good trick.
Yeah, and so that's just their first step. Let's go to the next one. What do they do
next step? They divide everything into 8x8 blocks, and then they treat each 8x8 block differently. And then in the end, you assemble them back, right? So. This is more like of a wrapper.
Would be like a 8x8 pixels. You can think of it that way.
8x8 pixels. Yeah, it just converts them into like little tiles, right? And really, this is like, I don't think it's like particularly clever. It's just like you kind of have to do this to get the other things, right? It's like it's almost like a wrapper, right? It's not that exciting. And it's pretty simple to work with, right? All right, then we get to the discrete cosine transforms, and those are like again really clever things, right? So discrete cosine. So you can make, so imagine these wave here is a color, right? So you can actually basically encode this wave with sine waves, right? And you just kind of layer them on top of each other. It's just a common thing for math, right? Yeah.
This one's a little bit harder to understand. I would, at least for me,
Yeah.
but I think what it amounts to is that you can take a very specific curve and approximate it with way less byte, or like way less info, and that approximation.
Maybe with the same info in our case, the way less info comes next. Yeah, but like it just converts it to a different form.
Yeah, that's true. The quantizing. Yeah. I'm blurring it a little bit.
Yeah, and then each sine wave that's like part of this, right, has some sort of coefficient, right? And that's the important part. So in JPEG, it actually is like a 2D version of this, right? Where you have the sine waves going in every direction, right? Which is like crazy. It's like hard to see, right? Hard to understand, but that's what it does. Yeah. And so then what you do, every little 8x8 tile can be composed out of any number of these waves, right? You can have like one of this wave, two of this wave, three of this waves, right? Just like different waves. And then when they all combine together, you get your own tile. Yeah. So that's the discrete cosine transform, right? Kind of complicated. Then there's also quantization step. That's like kind of this step next. So I think quantization just multiplies something. Then we have the zigzag, right? Just multiplies every coefficient by a value, which is again kind of further compression of the DST coefficients.
Yeah, I think this is where another part of the quality JPEG setting comes in. Is like the lower quality you pick, the more it gets quantized, and what that means is like the more precision that gets kind of thrown away.
Yeah.
Usually in the more high frequency stuff, which we can show in just a moment.
Exactly. Yeah, and then we get the zigzag, which I think is another clever way, right? The way these one like are encoded, these little tiles, is they actually follow like a zigzag pattern, right? In the bit stream, right? And then what this allows you to do is that basically the low frequency patterns like this, right? They come up first, and then the high frequency, which has like all these many details here, they come in, last, like in the order of things. So, but what the quantization steps allow us to do, it's kind of like turns them all to zeros, right? Right. Am I explaining this right? Yeah.
No, yeah, you are. Like, so basically, as you move your way down towards where your cursor is, you're getting higher frequency, which generally humans aren't as good at perceiving. And so the quantization step makes it so that more of that information is thrown away than the information in the top left.
Yeah.
And so by following a zigzag, you can basically get more zeros in a row. Because if you went linearly, you'd basically if you follow your cursor along, right, you'd want to start throwing away things on the right really soon, but you'd have to go back to something you want a lot on the left every time, and so you'd have shorter runs of zeros. The longer you can make those runs of zeros, the better it compresses, because you basically have like number, and then like 100 zeros. Well, not 100, but like 40 zeros. Well, 40 zeros is very compressed compared to the specific value for every pixel. And so that's just another trick, is they can basically take 64 pixel values, which they need, and they can encode it in basically like 32 or less numbers. So it's another divide by 2, you could say, approximately.
Yeah, or more even. Yeah, depending on the quality. Yeah.
With very, obviously JPEG is lossy. You are throwing information away, but done right and done once, it's so clever.
Yeah, it tries to throw the information that human eye does not care about, right? Like the number of grains of sands, the exact position of the blades of grass, like those things just humans aren't good at like seeing or perceiving. We just see, a field of grass. We don't see each individual blade of grass, right? Yeah. And this removes it right away, which is like...
And in specific, we don't see the one slight like RGB 253 versus... or let's say green 253, green 254, green 253. We can't even see that. So this just throws that away, turns it all into 253. Yeah. For example. Yeah. Right.
So really, really cool, really clever, right? And this format is pretty old. It's like from the 90s or something, right? 93.
I think. I don't want to say a date, but it's old.
Okay, yeah, it's like
they were
old.
smart.
Yeah,
Smart.
they were smart back then. Yeah,
Yeah.
pretty cool.
Back then.
Back then, yeah. Well, I don't know. Okay,
Anyway.
then let's talk about how it's like laid out in binary. So if you imagine this is the bytes, this is like 64 bytes long, and there's like individual bytes. It all is laid out in chunks, right? And you can even look at the code and how chunks work. But yeah, it's pretty simple. You start out with like the header chunk, then you have another chunk, another chunk, another chunk, right? But then they have
Each chunk has a name or something. Right?
yeah. Each chunk has a name and like a length that like actually like very easy, pleasant to work with, right?
Yeah.
And then there's this chunk, which is just like okay, and then comes just like a blob of data that has no name, no length, no nothing, just like blah, right?
Yeah.
And majority of the image is stored in this kind of like wild west of bytes almost, right?
Yes.
And then while you're reading, you have to watch out for the special byte pair to appear at the end. Kind of like, I know, like in C, like the neural terminator for strings. You just kind of read the string till you like hit it, and then you're done. It's like so gross. I think like just it took us a while to like even figure out what's going on, right? It's like
it's even more complicated because this is not byte encoded data, right?
Yeah.
It's bit encoded.
Yep.
So you're reading like 3 bytes, 6 bytes, 12 bytes, 3 bytes, 6 bytes. Oh, so it's not even like you can scan it looking for the 2 bytes you want, because those 2 bytes you want might not be on the byte boundary, although maybe the spec says they have to be.
I think they're on the byte boundary. Yeah, you can look for the exact bytes, but yeah, still, it's like super annoying.
It's very complicated because it sets such a nice standard, right?
Yeah.
Here's a chunk. The chunk is this long.
Exactly.
Great. I can jump to the end to the next chunk. Except you get this, and it's like, I
Why?
guess I have to start linear scanning.
Exactly. Yeah, I have to just like just like yeah. If something fails, it means you bail out of this thing. It's like so weird, right? It's like, especially if they had a system, they could have just put a header and a length on here and it'd be fine, right? Like no problem.
But anyway, we did figure it out. It's just kind of one of those dramas of the file format.
Yeah. Do you want to go through the chunks, like what they have? Yeah. So this is the file format. Right? Yeah. Let's go scroll to the very bottom, and this is like and this is the chunks, right? It's like here's how decode JPEG works. You start out, you have a string, and then you have the chunks. So just read the chunks like starter frame, simple chunk, different starter frame, because there's like different types of JPEGs, and so they start with different frames. Then we have our Huffman table, which is used for Huffman decoding. We have our start of image, end of image. Like we have the restart markers. If you run into them here, something went wrong. But they are kind of like almost, I think, these table markers in a way. They feel like it, but they aren't, right? Which actually took me a long time to figure out. I wanted to make like the restart markers work like chunks, but no, they're like crazy, right?
Yeah.
Then we have our quantization tables, our restart interval stuff, start of scan, and this is where that entropy encoded data comes in. So you get your start of scan, it's almost like part of this chunk, but not, because the start of scan chunk states that it's only this part, right?
Yeah.
But really after that we have the entropy encoded data that is kind of like Wild West. Bytes just appear here, deal with them as best as you can. It's so weird.
Yeah.
Right? Yeah. And then we skip a bunch of chunks. We decode the XAF chunk, which is like we'll talk about that later. Yeah, we skip a bunch of comments chunks. Yeah, and if we have an invalid chunk, we are out. Yeah. Anything more you want to say about the chunks?
Well, I think the big thing here is just that there's a lot of different chunks. You read each one, and they give you a little bit of the info you need in order to be able to process the image data itself. And what's nice about them is, like you said, they're clearly delimited, so you can just go in there, read some values, and move on. It's really just entropy encoded stuff that gets complicated. Yeah. So let's go back maybe to the images, and we'll move on to the next step.
Yeah. So the next complication. So this is basically the first time when you did the JPEG format, right? Is basically you got really stumped by this, right? And it's just not worth our life trying to figure all this like entropy encoded and progressiveness out, right?
Yeah. But I can precisely tell you exactly how I felt. So I figure out how to get all these chunks parsed in the Huffman coding, and like I could even load like a basic RGB JPEG, right? So I was all like, oh, I figured out JPEG, ha ha ha, I'm so good. And then I go and like, well, I should make sure I can load JPEGs from the internet. And the very first JPEG I grabbed from the internet is a freaking progressive JPEG, and it doesn't load. And I'm like, why do people even use these anymore? And then I go and look how to decode it, and it's a nightmare. And then I was like,
the spec is like obtuse, right? It's like, what's going on?
I remember saying down there, like, you know what? Let's just come back to this. This looks like a pain. An STV image is great. and it proceeded to stay that way for like a year.
Yeah,
But
yeah,
then Andre showed up and
uh,
decided to go to war with Progressive,
yeah,
and so
yeah.
you can take over
Exactly. For
from
some
there.
reason, I was just like there, and I'm going to defeat the JPEGs, right? And yeah, I basically just took your files that were already working. Like they could like parse maybe not maybe like 25% of JPEGs out there, right? Probably something
Yeah.
like that, right? They could already
Hmm.
work, right? It's just like this progressive stuff was like just needlessly confusing and complex, right?
And restart markers, which we'll also
Yeah,
talk
which
about
we'll
too.
also
Yeah.
talk into. Yeah, and it's like both of those things are just like what, yeah, and yeah, just basically grounded and grounded till we figure it out.
Yeah.
It's like we basically had the full J, like the cool parts, what we think was like the clever parts, we had
Yeah.
working like really quickly, right?
Yeah.
Or like what would someone would think are the complicated parts of the format, right?
Yeah.
The transforms, the chrominance stuff, the zigzag, right? We had that working like almost at the start, right?
Yeah.
It's like this wrapper stuff around it. It's complicated.
Yeah.
The progressiveness and the restart markers. It's like if you want to read all the JPEGs that kind of exist, right? You have to figure this out, right?
Yeah.
Yeah.
And it's the thing that really was kind of unmotivating about it, to be honest, is like progressive is just a bad idea now anyway. Like people
Yeah.
just shouldn't even be using this. And
Yeah.
same with restart markers. Like
Mm.
these are like legacies of maybe a different time, which you can defend in a
Yeah,
moment.
yeah, we could,
But
yeah.
but today, I don't think they're worth it. But for some reason, there tons of images out there are encoded with them, and I'm sure JPEG encoders in various image editors still encode them because that's just how they were set to do it 20 years ago.
Yeah,
Right?
yeah,
So,
exactly. Yeah, the progressive one. If you don't have so JPEG can either be progressive or not progressive, right? So if you get a non-progressive JPEG and it loads in small connection, you kind of get this kind of like loading, right? Kind of
Yeah.
like it just loads from top down as chunks come in. You can decode them and render it, right? We don't do this, right? Like some library can do this. We don't, right?
yeah, we just
Uh,
load it once because
Yeah, because computers just fast enough. Even so, but if it's encoded progressively, it kind of has these kind of like, different layers to it, right? So you can load it in stages, right? Which is nice if you have like a slow connection, right?
yeah,
Yeah,
perhaps.
perhaps, right?
Debatably.
Perhaps nice, right? But currently, what websites do, they actually give you a separate image. That's just like a blurred out version of stuff. Like we don't do this anymore, or like sites try not to do this anymore.
Yeah.
What you do instead? You have like a blurred version, which is like even more compressed, and you just wait when the image loads fully, and then you pop in the full thing. So this
Yeah.
blurred and like pop in is like very common on common websites, and I highly recommend people to do that instead of relying on some sort of progressiveness of JPEGs.
Yeah.
Yeah, that's what I would recommend there. Like, there's still a need, I think, for this kind of progressive loading. It's just I think we just solve it differently now.
Yeah. Yeah. Instead of building it into the file format, you just like compose two different images. You switch
Yeah.
from one to the
Yeah.
other, and it's very simple. Because then you can make two simple images, one of which is hyper compressed because it's like
Yeah.
just a blur. Right?
Exactly. Yeah. Even
And
more
then-
compressed than this thing. Yeah.
Yeah.
Mhm.
And then you just snap in the nice one. The decoding time is instant, basically, from
Yeah.
the perspective of a user. So there's no need for anyway. Yeah.
Yeah.
So it was cool. Maybe at some time we
Yeah.
have better
Yeah, in the
things,
90s,
but-
early 2000s, like, yeah, before we figured out the blur trick, right? But no one even uses the blur trick because, like, no one cares, right? This progressive is
Yeah.
just kind of a historical relic, I think, at this point. Yeah?
Yes.
All right. Yeah, and this is how it's stored in the thing. It's, like, even more custom. So we have our normal headers that we like, right? Little chunks that are, like,
Yeah.
easy to read. Then we have this, like, weird data with a weird, like, marker, right? And then it, like,
Yeah.
ends. And then you get another, like, block of this entropy encoded data, which is encoded slightly differently because it's, like, additive, right? This is like the start, and this is like the additive. So it's like encoded slightly differently. And yeah, and we again like another blob, like we have to watch for this marker, and then another like blob, watch for this marker, another blob. And just like so like laborious and like confusing to read because you don't know where anything starts or ends. It's just kind of like when it breaks, you start a new thing. It's like what? Yeah.
Yeah.
Yeah. They like would have been so much happier if they just had headers on these things.
Yeah.
So-
Simple things would help a lot.
Yeah, it's like you still put 2 bytes here. It's not like you would have even used that much space for headers.
Yeah, I don't actually even know if they're like why that was chosen. Maybe
Yeah.
there is some reason, but sitting here today, having written the decoder, like
Yeah, we're just
it's
like
not
puzzled.
quite clear.
We're just
Yeah.
like puzzled why they did this thing. Yeah, crazy.
Yeah.
Yeah. Next thing that there also exists is the restart markers, right? So originally, when I talked to you, I thought restart markers were to be used for threading, to like, because computers were slow, so you can use multiple threads on every restart marker to kind of read your stuff.
Sure.
After looking into it more, I don't think it was related to threading. It's related to like degradation, right?
Okay.
So here's an example of image with no restart markers. An even slightly degraded image will basically be unusable. You'll not see what's going on, right?
Sure.
But an image with a little bit restart, like some restart markers will probably look like this, right? If it's degraded slightly, because it has some, so you can restart, right? But you can see kind of here, like, was walking along, decoding, and then I, like, hit something bad, and then I, like, couldn't decode anymore, right? So the more restart markers you put, the better the images can transfer with, like, degradations internally.
Lossy transfers or lossy storage.
Basically. Yeah,
Basically.
lossy storage. Like, but it's just like not a like maybe it exists somewhere, like with like radios or something, or like sending images to space, right? Yeah. But like we just have protocols that handle this, right? Like almost nothing on the modern web can survive. Tolerate. Like exactly, like garbled data basically almost ever, right? Or even if it does, it like does it through some sort of resend systems, right? Where it like some
just
sort of like bits
again.
Exactly, right? There's this like right. It's just kind of weird to have that inside the image format, not into some sort of like handler that handles it outside, right? Yeah.
And again, maybe there was a universe where this made sense at some point, but sitting here today, these are kind of like the bummers of writing a JPEG decoder. Is these things are like they don't make sense anymore, but they have a huge price if you want to write a new decoder because you have to figure them out.
Yeah, exactly, right? And again, the entropy encoder, like even is more problem, right? Now you not only have like this restart marker or whatever, these like end of entropy chunk markers, right? Yeah. You also have restart markers that just kind of randomly appear in your entropy stream, and then you have to like deal with, right? And it's just like it's so weird. You get a chunk, and then like just like, and then there's like okay. You have to have the start version because you get hit a restart marker or it restarts everything. So you have like the restart version of this entropy encoded data, and then again deltas basically right on top of it, right? Yeah, crazy.
Yeah, so progressive plus restart markers is kind of like pain.
Yeah, exactly. It took forever to figure it out. Like, and the spec, if you read the JPEG spec, right? It's
enormous.
It's enormous, right? It kind of tells you like what they are, right? But it doesn't like kind of tell you how to parse them or how to think about them. It's just weird, right?
Yeah. This is actually going back to that video we talked about.
Yeah.
A lot of this stuff just seems random and arbitrary if you don't know why it's
happening.
Like, why the zigzag? You know, like what are we doing here? You know, was like a linear scan not good enough or something? Turns out there's like a really good reason for it, but nobody like, at least I don't feel like it was obvious until it was made obvious. So.
Exactly, yeah. And again, with the progressive and the restart markers, like we personally don't feel it's a good reason. It's not clever for us, right? It's not clever enough for us anymore to kind of, signify the pain, right? Yeah.
Exactly.
And even if they wanted the restart markers and the progressive stuff, right? They could have made it easier to parse for sure, right?
Agreed as well.
Yeah, because it's just like, they waste bytes in other ways. It's like, why are you wasting these bytes? And then like here they're like, oh no, you gotta pack every bit in, right? It's just kind of weird. Right? Yeah.
Complicated format, that's for sure.
So that's that. Yeah, another complication, right? Kind of separate is this XCF stuff, right?
Yeah.
Yeah, so the XCF stuff is interesting. It kind of comes from the TIFF, another image format. So it kind of has like its own TIFF header and even like its own like Indianness, which is so weird. Like just come up with your own table. Why use a TIFF table? It's so weird, right? Like why do you bring another image format into this, but not the image of the image format, just like the headers? Yeah. It's so weird. So the only thing we really read from the XCF is the orientation, because that's important. Turns out like a lot of JPEGs are just like oriented differently than what they're stored. Yeah. And I remember reading an article, the guy just like saying that's dumb too, because it's like why, like I guess it was maybe made when you're like looking at like a viewer and you want to just like in a camera, and just a very cheap operation to orient something differently, right? Just like change one byte and it just moves, right?
Yeah.
But computers have so much power, it's just so easy to just re-encode the image. It's so weird.
Agreed. It's just so weird.
Yeah, just so weird. Yeah. Yeah, and I think
we have to figure it out. So.
And I think the guy in the blog post was saying how you can losslessly rotate the image and it's fine, right?
Yeah, and that makes sense as long as you're not doing any resize or whatever.
So this orientation is also kind of like some sort of effort saving in the
That's
past,
true.
and
Because you
now
really
it's
can't
no
re-encode a
longer.
JPEG
Yeah,
without
yeah.
losing data. So
No, you could. I think for rotations you could. Yeah, you could rotate every quantization table and stuff.
sure, I see
Yeah,
your point.
yeah. I think it's like you can losslessly redo this. It's just like no one, like it's just like in the past they said, oh, that'll be hard. Let's just put an extra thing in there and let it go, and then everyone has to like use it and know about it, right? It's just not clean, right? Yeah, yeah. I don't like this orientation stuff. There's other stuff in the XCF we can look at, potentially read. Like there's, I guess, like brightness values and etc. There's uh,
Yeah.
like whether your pixels appear on the edge or the center, called the cosite stuff. We did not implement that because we actually didn't find like any JPEGs that like use those features. So yeah, I think it's fine.
Agreed.
Yeah,
Hard to,
yeah,
hard to do something and know it's right if you can't test it. So
yeah, yeah. STB doesn't even read this XCF stuff, right? It doesn't do the orientation. So like this is already like over STB stuff. And if it's good enough for STB, it's probably good enough for us, right?
yeah, we honestly orientation wasn't even something we were really gonna do. I think you just noticed it and was like, this is kind of a missing
Yeah.
feature. So you just went and implemented it,
Yeah,
right?
yeah, yeah. Because there are actually like images with different orientations out there, right? Well, different images with like a different cosite stuff. I've never seen it. Like, if you have one, send it.
Yeah, sounds good.
Yeah. All right, and then I think we have the testing. Yeah.
Yeah. Well, so everything we just talked about is very complicated. Hopefully, some of it made the slightest bit of sense. Again, we'll link to the video that will help kind of do a much better job of adding the visual side to it. But you got to test it, or you have no idea if you're doing any of that right. There's no way to know without literally seeing the correct output image, basically. And so we put together a big blob of like all of the scenarios that we could kind of like run into are basically iterated here in the test files. Is that right?
Yeah, exactly. So what happens here is that, yeah, basically we had more images, but we just throw away because a lot of them basically test duplicate stuff. Like we feel like this is like a minimal set of images that tests everything.
Yeah. And by everything we mean progressive versus non, restart markers versus not, incorrect encodings, grayscale, the different levels of compression of the chrominance and luminance channels, orientation. You know, there's just a handful of like you could think of as like branches that you got to just cover.
Yeah.
And so here they are, and they help us be relatively confident. I mean, we've tested more things than this, but this is kind of our long-term sanity check.
Exactly. Exactly. Yeah. If you run this on every commit, so if something breaks, we'll know.
Yeah. And so yeah, we're pretty sure that there's a lot of JPEGs out there, and we can probably load it.
Yeah. Yeah. Exactly. Which is great. Yeah.
It's awesome.
Yeah. The other stuff we also do is fuzzing, and you did this mostly, right? Like you the pioneer in fuzzing for Pixie. Yeah.
Yeah. It came a long time ago from just some performance goals that I had. So one of the kind of classic problems that C have is like buffer overflows, overruns, reading past the end, seg faulting, all sorts of kind of crazy things that can just cause your program to just go explode, right? And you have no idea what happened or where it happened. Very difficult to debug.
Yeah, integer overflows, and all kinds of stuff. No pointers, yeah.
So NIM, by default, when you compile a NIM program, even with release mode, it generates all sorts of checks like, make sure you aren't trying to access an index past the end of an array or something. I'm not sure which ones still get compiled in even in release mode. I know danger throws them all away, but that's across the entire compilation, which is extreme. So what we've done is, well, let me explain why too. So those checks are great. However, they do have a price. So, every code and every branch you make, it slowly accumulates in performance, and if you want to be good at loading images or other things that are just very complicated, data-intensive things, you don't really want it to be any slower than it has to be. And so what we've chosen to take on is we will turn checks off and basically live in C++ mode for these chunks of code where performance is critical. But then, to feel confident doing it, we will fuzz the JPEG decoder, the PNG decoder, these other things, to make sure that no matter what data you throw in, it will not do the wrong thing. It won't read past the end of the buffer. It won't, do other bad things. And fuzzing is the kind of thing where, well, let's say these errors are very difficult to see just by reading code. You can't really always know if it's a safe read or not. So instead of trying to reason about it, which is faulty, what we do is what's called fuzzing. And fuzzing is for example, you take a perfectly good JPEG, and then you just poke one byte with a different value. And maybe that one byte will change a pixel color, but maybe it'll change a length of something, or a code you're supposed to read, or some really important value, and all of a sudden it'll be out of the bounds you expected it to be. And so fuzzing will draw those things out because computers are fast, so you can run a million different variations of a JPEG image across your decoder and make sure it doesn't blow up no matter what you send in. So that was a bunch of words to just say we've been able to kind of increase and be competitive in performance with loading some of these things, but without having to sacrifice the safety that NIM offers for your normal compilation. That kind of makes sense, Andre?
Yeah, exactly, right? And the process we follow is we fuzz everything kind of in like debug mode with all the checks on, right? So if something bad happens, we know it, and so we have to like put an if statement usually, right? Usually it's like checking that the length are like what we need, right? And so
exactly.
And then once basically our system never crashes, no matter what junk we throw at it, right? It just kind of shows you invalid, right? It just gives you an error. Only once, like it is basically safe. We've like proved it to be safe, right? Only
as
then,
best as we possibly can.
Yeah, only then we put this push checks off on, right? And then we basically kind of like ascertain that it's not crashing in those areas. So only then we do it, right? Because pushing checks off is very dangerous, but also very performant, right? So it's like we want the performance, and we spend the time to get it by fuzzing and doing all this stuff.
Yeah. And kind of a fun thing that I think we've both noticed about fuzzing is that you'll not know what's wrong, and you'll start fuzzing, and you'll run into it in like 10 seconds.
Exactly. Yeah. It's so
this does not take very long.
No, it doesn't. It doesn't.
At first. At some point, it starts to get pretty rare. But at first, it's just like instantly finding holes all over the place that you don't even notice, and it's kind of fun and good feedback in a way where it's like, oh, of course it would need that, right? Like I forgot to check that the buffer needs to be long enough to read another 4 bytes or something, right? So
exactly. Yeah, and also integer overflows. Like you add two integers together, especially since JPEG uses so many 16-bit integers, right? And for speed, we do use 16-bit integers. They can't store that many values, right? So when you add one 16-bit to another, it is very common for them to just overflow, right?
Yeah.
So NIM actually checks that, which I think is great. Like C++, they don't care. They just blow past it, right?
Yeah.
But it's slow. Every addition has to check, right? It's a branch, right? We don't want those branches. So that's why we fuzz, right? We make sure those values don't overflow.
Yeah, or if they do, because sometimes it's okay if you expect it to. Right?
Yeah.
You just have to be consciously choosing what's happening.
Yeah, exactly. Yeah, I think in C++, people just don't think about integer overflows that much, which I think is a big shame. We've thought about them.
Yeah. And so so what this means to you as a user of the Pixie library, if you decide to give it a try for loading JPEGs, is it's very well tested, and you can expect to really not have any trouble. We can't guarantee every JPEG will load, but if it doesn't load, we'll do the proper NIM thing, and you'll get an exception, and you'll know your program won't just randomly stop running.
Yeah, exactly. Yeah. Another thing with so fuzzing is important to reading untrusted JPEGs, right? Another thing to reading untrusted JPEGs is I think like the size, right? So when you get a JPEG from somewhere, right? First you can check that it's not huge. Like if it's like 12 megabytes or something, you can say, hey, only 2 megabyte JPEGs allowed, and you could just throw it away, right?
Yeah.
But because when you read the JPEG, it does allocate a bunch of buffers. Someone could have an attack on you where they send you like a tiny JPEG, but asks to like allocate a whole bunch of memory, right? And then it basically breaks your servers, right? So what you can do is we have this dimensions call, which basically just reads the dimensions of the image, and so then you can choose whether you want to proceed or not, and you make sure that the dimensions call will not allocate,
memory or something.
Yeah, well, it might allocate some memory, but it will not allocate, like unbounded amount of memory based on the JPEG, right?
Yeah, exactly. I think that's the key thing is that whatever image dimension call does, which currently is very little and shouldn't ever change,
yeah, exactly.
it will never behave differently based on the size of the image.
Mm-hmm.
Whereas the decode clearly needs to.
Yeah.
If you want to decode a big image versus a small one, you're going to use more memory versus less. We can't magically not do that.
Yeah, and it's going to be slower, right? Yeah.
Yeah. And so you could imagine, like, I think you kind of hinted at this, and I think it's a perfect example. Like, let's say you're running a web server and you want users to upload images to use for their profile picture, right?
Yeah, very common.
Great. But they might upload a 1080p image and like, well, you're probably not going to show it that big. So maybe you want to resize it to 512 by 512 or something, right?
Yeah.
To do that, you have to read the image.
Yeah.
Reading and decoding the image means doing all that memory work. So you can imagine a user coming along and saying, this site parses images. What if I made a poison JPEG that says that's, a 2K file, but the very first thing it says is, what's my width and height? Oh, I'm 10 million pixels wide by 10 million pixels tall, right? Well, that's a problem because that's more memory than your server has, for sure.
Yeah.
And so, your server might just crash out of memory and you'll spend hours, days, weeks trying to be like, why are people crashing my server? I don't get it. What's going wrong? This allows you to put in bumpers there, right? It's like, why is this image larger than maybe 4,000 pixels wide? That's no one has bigger than 4K images for any good reason. So, and then maybe you want something smaller. It's up to you, but you can enforce it really easily for untrusted stuff.
Yeah. And maybe you're just like, I don't know, do a listing of images, right? You just have like a bunch of images and just want to know their size to display, right? Like on a file viewer or something, right? Like another good way, just very free, basically free call, right? You don't have to parse the whole image. You can just like ask it for its size.
Yeah. So we have both of those APIs where you can load the image itself, get the true pixels, or get the dimensions. And I think you even have an example file of showing how easy it is to read a JPEG. Maybe we can show that real quick.
Yeah, sure. Well, it's just Pixie stuff, so yeah. Just read it, yeah.
Very
Easy.
simple. I mean, can it be easier than one line? Yep.
Yeah. In Nimble, install Pixie, import Pixie, right? Let's read image, whatever the image path is, you get the image. And then you could do a whole bunch of stuff, like the entire Pixie is available to you, right?
Yeah. And of course, read image is the file version. We also have decode image if you have a data blob.
Yeah.
So you don't have to write it to file and read it from file or anything crazy like that. Yeah. We're just showing the file path version here because that's pretty common use case.
Yeah, exactly. Once you have that image, you can do whatever with it, right? You can like upload it to, if you're a game, upload it to a texture, right? You can maybe put some words over it with the rest of the Pixie commands, right? You can like scale it, resize it, flip it, do whatever, right?
Yeah, exactly. Like once the JPEG is in Pixie, the whole world is open to you. The real trick is just being able to go from that complicatedly encoded JPEG into just a flat RGBA buffer, which is what Pixie is.
Exactly.
So maybe some closing remarks here on JPEG. We joked about this before, but I really think it's a good line. Is JPEG, like the people who made it, they did like a really good job of coming up with smart tricks to make files small but still load really good, even if they're very complicated real world images, which are really hard. Like PNG is way worse, way bigger files. I mean, but there's a problem with it, which is kind of what Andre fought, right? Yeah. Which is that the actual literal binary encoding leaves something to be desired.
Exactly. They just like wrap their clever ideas in kind of like a meh system, right? It's like, I was like, why did you do that? Just like, they could have just like made small things like headers and links, right? That made sense. And then it'd just be so much easier. But no. And then I guess like why include like progressive and the basically, and the other stuff, including progressive, restart markers, and the orientation like separately. Just like meh. Not a great idea. Maybe it was a great idea in the past, not anymore.
Yep. But yeah, so this is kind of our little rundown of what we did with JPEG and Pixie. And, I think we both had a hand to play in it. I give Andre the credit for sure for overcoming the, like, really hard part. I basically was like that GIF where the guy just, like, disappears into the bush. I saw progressive and restart markers, and I bailed.
Yeah, and this is what a lot of people do on the internet. So I found, like, a lot of, like, tutorials, or at least people explaining how to read JPEGs. And they all start out, like, Yeah, and they basically just get halfway through, right? Yep. And then they kind of done. All right, I loaded like a JPEG. I'm done.
I loaded a JPEG.
Exactly.
The easiest one.
Easiest one, right? I don't care about restart markers. I don't care about progressive. I don't care about orientation. They just kind of right? Done, right? It's so weird. Well, it's not weird. It's just maybe like human nature. But like
Yeah.
almost all tutorials out there are kind of like unfinished. They only get like the fun, clever parts of JPEGs, and then they stop. They don't go with because it's just hard and stupid
Very
and
complicated.
unnecessary, right? It's like yeah, they don't go for the restart markers, and they're just like so weird.
And even then, I don't really think there are that many JPEG decoders in the wild.
Yeah,
Like,
yeah, exactly.
that actually even work in the basic sense.
Yeah.
And so that was another thing that I think made this a little difficult. Is it's not like you can just go and look at 12 different implementations and kind of take what you like from each one and learn from them and then write your own kind of using that guidance.
Yeah.
There's basically STV image, which is very difficult to read C in a huge file that does a bunch of file formats, which is, again, it's amazing, and I say nothing bad of it at all, but it's difficult to learn from. And then there's libjpeg, which, God forbid you look at that. And then there's a few, like, token decoders that kind of do a little bit, but,
Yeah.
it's mostly you're on your own.
Yeah, I would say the token decoders are like easier to learn from, right?
Yeah, until
but
you get to the hard part.
yeah, until you get the hard part, which they don't even implement. The exercise of implementation is left to the reader or whatever, right?
Yeah.
Classic.
But again, it's better than nothing. I mean, truly, these are people, they wrote something complicated, they made it open source. It's awesome.
Yeah.
But
it's great.
it left something to be desired when you were trying to figure out progressive.
Yeah, exactly.
I bet.
Exactly,
So.
yeah. If you want to write your own JPEG decoder in like some other language, right? Like, yeah, reference ours. Like, I hope we made the code clear enough that it'll be easy to follow.
Yeah. And where it isn't easy, know that it's probably a combination of because the file format's complicated and we haven't come up with the cleverest possible simple way to do it because it's complicated.
Exactly.
So we tried. I'm sure we'll change it over time.
Yeah.
We do think it's a pretty good one to learn from compared to maybe some other stuff.
Yeah.
So. And it's easy to use, and we're, again, like we said before, I think we're pretty proud of it. So, unless you want to do some more remarks, I think that's kind of all we have to say.
Yeah, that's it.
Thanks for watching.
Yeah, thank you. Bye.